Okay, in this video we're going to consider the process of reducing a set of functional dependencies to, if you like, its simplest form. And we'll call that simplest form a canonical cover or a minimal cover for the set of functional dependencies. Okay, so in the lecture notes we see that there are 3 steps involved in producing that. So we take our initial set of functional dependencies and we transform them so that all of the functional dependencies have a single attribute on the right hand side. The next step is to get rid of redundant attributes from the left hand side, and the final step is to go through the set of functional dependencies which we've produced from these 2 steps and end up with our canonical cover. So we're eliminating the redundant functional dependencies. Okay, so let's take a look at this example here. So we've got 6 attributes and 3 functional dependencies. So according to step 1, we want to make sure that all the functional dependencies have a single attribute on the right hand side. Now this is relatively straightforward because we saw from Armstrong's axioms that if we've got something like A determines B and A determines C, then we can transform that to A determines BC. And you can also go back in the other direction. So this first dependency can be pretty easily transformed into these 3 dependencies. And similarly, the second functional dependency can be transformed into these 3. B determines E. Now the final one has only the final functional dependency has only a single attribute on the right hand side, so at this stage that can't be transformed any further. So this is our new set of functional dependencies after step 1. So perhaps I should put that after step 1. Okay, the next thing to look at is, are there any redundant attributes on the left hand side? Now, any functional dependency that has only a single attribute on the left hand side can't have redundant attributes on the left hand side, because if you remove the single attribute, the functional dependency goes away. So the only functional dependency we really need to consider here is A, C determines E. And what we're looking for is, if we remove either of those attributes, do we still have effectively the same set of dependencies? Okay, so let's say for example that we remove C. So we want to try, can this dependency be replaced by that? Well, if we look at the set of dependencies that we've got, we can't see that C doesn't determine anything, in fact, by itself. So the closure of this functional dependency is just C, doesn't involve E. So this functional dependency here is not a feasible functional dependency for the final set. The other possibility is that we try removing C from the left hand side, and if we do that, then we can actually infer this functional dependency from the ones that we're given. A determines B and B determines E, therefore A determines E. So after realizing this, we can remove C from the left hand side so that it's redundant, and that'll give us a set of dependencies like this. Okay, so the next step is to determine whether we can remove any of these functional dependencies, and what we're looking for is that one or more of these functional dependencies is determined by the others. So we could start out by saying, alright, is this functional dependency here redundant? In other words, if I remove that, could I infer it from the remaining functional dependencies? And if you look at them, it's pretty clear that you can't. A determines C, determines D, and that's as far as you can get. So the closure of the set of functional dependencies starting from A is without B is just C and D. So that dependency is not redundant. If we look at the next one, then we can pretty easily see that we could infer this. A determines B and B determines C. So we don't need to explicitly state that A determines C. We can infer that from the remaining functional dependencies. Okay, A determines D, same reasoning. A determines B and B determines D. Therefore we can remove that from the set of functional dependencies. What else can potentially be removed? Okay, A determines B, B determines E, A determines E. So there's clearly some dependencies involved there, and the functional dependency that could be removed is this one. You can infer that from the fact A determines B and B determines E. So that would leave us with a set of dependencies that looks like this, and none of those dependencies can be removed without actually changing the closure. So that's the final set of functional dependencies, which actually occurs at the end of step 3. Okay, so that's an example of producing a minimal cover.